Today we will be talking about different wave phenomena for AP Physics 1. So one of the main ideas is resonance, and that is when essentially you have two objects, you make one of them vibrate at a frequency that matches one of the natural frequencies of the second object. And that first object that's vibrating forces that second object to vibrate at one of its natural frequencies. So essentially, different objects, different materials have what are called natural frequencies based on the material and the structure. And if you bring something in contact with it or close to it that is vibrating at one of its natural frequencies, you can force that object to vibrate. So in the GIF here, you can see someone holding, it looks like three different objects, and they're just shaking their hand. In other words, vibrating their hand at some random frequency. And that object closest to us is vibrating a lot more than the other two. So that motion of the person's hand is forcing that closest object to us that's moving a lot to resonate. So it is in resonance, it's being forced to vibrate at one of its natural frequencies. There are a lot of examples on YouTube of resonance. One popular example is, you may have seen before, someone singing into a microphone or just playing a tone that is able to shatter a wine glass. So whatever frequency that sound is at is matching one of the natural frequencies of the glass and is able to force that glass to vibrate and then shatter it. Another example you see a lot are people walking on bridges, or there's the famous Galloping Gertie. You can look up that bridge that collapsed. It's not exactly the same type of resonance we're talking about, but you can look up videos of people walking on bridges. If you have hundreds and hundreds of people crossing a bridge every day, their walking has a certain frequency, a certain rhythm to it. And if that matches the frequency of the bridge itself, you may have some swaying. So there are lots of examples of resonance, but the idea is you're forcing something to vibrate due to an object that is nearby. And architects and engineers have to take this into account when they are building skyscrapers. So there are some cool GIFs and stuff about that as well. When you have wind hitting it, if you have an earthquake, lots of different factors to take into account. We also have beats. So beats occur when two waves with just slightly different frequencies interfere. And the beat frequency is just the difference between those two frequencies. So the beat frequency might be 1 hertz or 2 hertz or whatever it is. So two waves with frequencies that are pretty close together. In the GIF here, you can see the red is the beat frequency. So you can see here we have, if this were sound waves, we'd have a loud noise and then a soft, almost no noise. And now we have a loud noise, and now we have a soft, almost no noise. So there's this beat frequency. If we played two tones that were close to each other and they interfered, you would hear it go like, wow, 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 wow. I have a demo that I'll put in this video of me doing this in class. You can kind of hear the beat frequency in person. It's much more effective, but my microphone on my phone was not very good. So you can see you have two waves of two slightly different frequencies, the lime green wave and then that blue wave, and they are interfering with each other. So where the crests and the troughs are adding together, you have constructive interference. So you have a louder sound, and then where the crests and troughs are canceling, you do have a quieter sound, some cancellation there. So that beat frequency would just be the difference between these two frequencies. And let's try to hear this and see if it works. First, what you'll hear is me hitting two tuning forks that currently have the same frequency. So it should just sound like two tones that essentially sound the same. Now, as you can see, I have two tuning forks that are the same frequency, but I attached these two objects to one of the tuning forks, and those objects allow me to just slightly adjust the frequency of the tuning fork on the left. So the two frequencies should be slightly different now, and when I hit it, we should hear beats. If I were doing this in person, you would really hear it. I will admit I didn't do the best job of hitting that tuning fork, but if you listen closely and maybe play it a couple of times, you do hear a change in volume. So the sound is getting louder and quieter over and over again. So listen a couple of times and see if you can hear beats for yourself. We've talked about resonance, we've talked about beats, and our third and final wave phenomena is standing waves. So standing waves occur when two identical waves move in opposite directions and they interfere with each other. I think it's easiest to understand them when you see them. So give me 1 second to give you some vocab and then we will look at some. So a node is a location where no vibration occurs, and an antinode is a location on the, let's say it's a wave on a string, so on the string where vibration does occur. I just remember this as nodes, no movement, and that seems to work. So here's a GIF of a standing wave, for example. So maybe this is just a string that's attached to a pole and someone is waving one end of the string. So standing waves, as you can see, it doesn't really look like there are waves traveling in any direction. Nothing looks like it's moving left or right. And standing waves actually don't travel in any direction. I think of them as kind of just flipping. Crests and troughs are flipping. But what is really happening is you do have waves that are identical that are moving towards each other and interfering. The result of that interference is what we call a standing wave. So it looks like the waves are kind of flipping crest to trough, but in reality, we really do have waves that are interfering. And standing waves occur at unique natural frequencies. We also call that a harmonic. So natural frequency and harmonic, those are synonyms. So I can't just take a string, attach it to a pole, and wave it at any frequency and get a nice standing wave. It has to happen at certain frequencies. If you have a slinky or a spring or a string at home, maybe have someone hold one end of it, put it on the floor, have someone hold one end and stretch it out. You vibrate the other end back and forth and see if you can figure out a frequency that creates waves that kind of look like they're just flipping instead of waves that are clearly going from you to the other person and back. You can create standing waves pretty easily doing that. So here are some drawings showing harmonics. So our harmonic number, I call that or refer to it as like the number of loops. It's the same as the number of antinodes. So in these drawings, what I have the first three harmonics. We're imagining just a wave on a string. So maybe someone's just waving a string that's attached to a pole or something like that. So our first harmonic is also called the fundamental frequency. So we have a lot of vocab here. We have natural frequency and harmonic, which are synonyms. And then the first harmonic we call the fundamental frequency. So if I'm imagining maybe the string is attached to a pole here and someone is waving it up and down on this side, when we create our first harmonic or our fundamental frequency, if we're waving it at the fundamental frequency, we will have one giant antinode, and then the two ends of the string will be considered nodes. So this part here is flipping up and down, and that dashed line is just meant to show that it's flipping up and down. So our nodes are areas of no movement. So the string actually isn't moving at the ends, but this is considered our antinode, and that's flipping up and down. So our first fundamental has, if you look at the picture, they kind of look like loops. So I usually tell my students, sorry, that's my cat. I usually tell my students, just look at how many loops there are, and that's the harmonic. So one loop, first harmonic, or you could think of it as one antinode, first harmonic, and we would just call that harmonic F with the subscript 1. Our second harmonic, so we have two loops or two antinodes, and now we have three nodes. We still have the ends, but now there's a node in the middle here. So if this were a string that was vibrating, I could take my finger and pinch the string right there, and it should not be moving. So we would call this F sub 2, and that is equal to 2 times the fundamental frequency. So two antinodes or two loops for the second harmonic. The third harmonic, so now we have 3 loops, and I totally missed labeling this antinode here. So there are 3 antinodes and 4 nodes now. We have another node here, another node here, and this third harmonic we could call F sub 3, and it should be equal to 3 times that initial fundamental harmonic. Now we could go to the fourth harmonic, the fifth, the sixth, and so on and so forth, but I just wanted to draw 3 pictures. So standing waves, lastly, they occur at natural frequencies that are equal to this equation here for a wave on a fixed string. So n times v over 2 times L. So n there is our harmonic number. So if you wanted the first harmonic, n would just be 1. V is the speed of the wave on the string. Earlier in the unit, we did get an equation for the speed of a wave on a string specifically. If you remember, it involved tension, mass, and length. And then L obviously is length. One interesting, important detail. In order to create standing waves on a string, the length of the string has to be a multiple of lambda, the wavelength, or lambda over 2. So you can't just have any length of a string necessarily and get the standing waves that you want. As you can see in this GIF here, if it's the first harmonic, that's equal to half a wavelength. If it's the second, that length of that string is a full wavelength. If it's the third, that's equal to 3/2 of a wavelength. So the length of the string is critical in order for standing waves to occur. It has to be a multiple of lambda or lambda over 2, which also obviously depends on what frequencies you're trying to get. So I strongly encourage you to look on YouTube. Normally I would do a standing wave demo. We have a wave generator. It's really cool, but since there is a worldwide pandemic right now, we can't do that, and I didn't get a video of it. So I will link a video or look up standing waves on YouTube, and there are lots of pretty cool videos of people creating them on strings. I think that finishes up our waves unit. I will be here if you need any questions.